there is a series of these lecture. I think we will cover all these contents hopefully in a 2.5 or 3 lectures starting from today. So we will generally start today with the stage efficiency, that what stage efficiency is and why it's important, and then overall stage efficiency, then maybe single plate efficiency. We will look at that how to calculate stage efficiency. Stage mean here you can say tray or the plate. So then when we have decided with the efficiency, and later on I will talk about it, after deciding the efficiency, you can calculate actual number of plates needed in any column. And after getting that, then we will jump towards the height of column, because when we know that how many plates we have to install inside a absorption or stripping column, then what will be the height of column. During this, definitely we will look at tray spacing and some of that stuff. Then after this, there are some calculations related to flooding velocity, what flooding is, when it will happen, and how to avoid it, or what will be the velocity that will lead it to the flooding, as well diameter of the column. They are definitely interrelated with each other, so they will be discussed. And at the end there is something about superficial velocity as well, tray layout. So these are the contents which we have to cover, and with this we will conclude, I think, discussion of this tray towers. Up to after discussing all these things, hopefully we have covered all major design uh, parameters of tray towers which are used for absorption or stripping. So today majorly I will talk about stage efficiency, and overall actually this is, I think, 6.5 section of your textbook. Yes, 6.5. So in this majorly covered is stage efficiency and column height. Hopefully this will not be covered in one lecture, because there are a number of things which we have to discuss. So by next lecture definitely this will be finished. Before I start the next topic, so quick revision or link it with the next topics, the things which we have discussed so far related to absorption. So after generally discussion about absorption, what absorption is, what are the parameters that you have to consider when you start the design, and what are some factors which definitely affect the absorption. For example, we discussed that there was temperature, pressure, and solvent which you select. So after discussing those things, then we started with the calculation of number of trays. So up to here, the thing which we have done is to calculate number of trays by using two methods, and one was called graphical method, or we can also call it Gauge method, and the other method was analytical method, and that is called Kremser method. So with these two methods we have studied that how to calculate number of trays, what calculation will involve when we have to you are looking for number of trays in any column, and these are called calculated or theoretical number of trays which we have done so far. So now we have to look for actual number of trays. In this we will see that either the number of trays which we actually need for some separation are equal to theoretical trays, or there will be some difference between these two. So what do you think?
So ideally they should be same, but in real cases they are different.
Okay, then okay, if they are different, what do you think that which one will be higher in number? For example, theoretical or actual?
एक्चुअल के केस में हाई रिक्वायर होंगी आई थिंक.
Yes, as compared to theoretical, actually you require high, and that is something linked with the efficiency of trays. So finally, when you have decided that how many plates are actually needed, then we will calculate based on that what will be the height of absorber or stripper column. So as I said that here, when we decide that we need, we said that we need actually more number of trays as compared to the theoretical trays, or the trays which we have calculated, they are called theoretical trays. By the way, if I recall properly, I think last week someone was, Abdurrahman, yes, maybe was asking about that there was a problem or some example in the start of chapter, and there he mentioned that number of trays are, I think, some number around 30, and there are equilibrium stages are 12. Yes, this was the case. So he asked last week. So there actually later on we will discuss that example maybe in tomorrow's lecture. So there when he is talking about number of equilibrium stages in this textbook, then he is talking about actually number of trays calculated by using some method. And when he said that number of trays are 30, that means that there are actually 30 trays in that example. In the start of chapter, I think in the first or second page, he has discussed that trays. So when we say that actually there are more trays needed as compared to theoretical, then what is reason behind this? So that is something called efficiency of the tower or efficiency of plate here, or stage. Stage means any tray or plate which you are considering, that is stage. So temperature, when you look at the vapor and the liquid which are coming in contact with each other on the surface of tray, so their temperature of vapor and liquid, which are, because when vapor and liquid will come in contact with each other, you know that then vapor leaves towards the upper plate and liquid leaves to the down plate through downcomer. So their temperature can be generally same until unless the vapor and the liquid which they are coming and they have already higher temperature difference. Otherwise, when they will come in contact with each other, most of the time the temperature of both stream when they are leaving from any plate, the temperature of both liquid and vapor is very close to each other, even in actual cases. Until unless just there was a huge temperature difference between them, then definitely they will not reach to the thermal equilibrium when they are leaving. But the other assumption which was like related to this, which we have considered so far, that when these liquid and vapor leave from the trace, their phase equilibrium is also achieved. Their composition of any component in the vapor stream as well as in the liquid stream, we consider that when they are leaving from the plate, they are in equilibrium with each other, and that equilibrium has been achieved. But in reality, when you look at these cases, so it is not necessary, and most of the time it is not possible that they will reach to the equilibrium, which is, we call it actually thermodynamic equilibrium, based on the K values that any component, for example, which we want to transfer from vapor to the liquid or the liquid to the vapor, that has been done on the any stage where liquid and vapor are coming in contact. So due to this reason, when you are not achieving actually thermodynamic equilibrium on each of the tray, it's mean the thing which you were expecting theoretically, that plate will be giving you some specific separation, that is not achieved completely, that is not achieved 100%, that will be less, although some component will be transferred from vapor to the liquid or liquid to the vapor. Actually, this I'm saying in case of absorber, for example, you want to absorb some component from gas to the liquid, so its transfer which you were expecting on any plate, that is not done 100%, because in reality they don't reach to the equilibrium completely. Yes, partially they can reach to it, but not completely. So due to this reason, then when one plate which you have installed that is not performing as per expected or as per the calculation, then it's mean that you will need actually more number of trays as compared to the trays which you have calculated by using some method. So we have to determine the actual number of trays in any column, and that will be adjusted in such a way that overall, like throughout the column, when vapor and liquid pass, we can achieve the required separation. Although the separation which we were expecting, for example, on the 5 trays. But as I told that when those on the surface of those 5 trays, when vapor and liquid came in contact, and you don't achieve that separation which you were expecting, then it's mean in order to achieve the required separation, we need some more plates. Because when we design any column, we want to achieve some separation, and until unless that separation is not achieved, definitely we have to repeat the process. So in order to avoid that, when you are designing the column, you have to then consider this factor, that in how many trays you can achieve the required result, the required separation. So then due to this, I said that there comes the concept of stage efficiency. So whenever any two phases like liquid and vapor phases, they are coming in contact with each other and then get it separated, so there will involve some efficiency of the tray or stage efficiency. So in order to look at this, that how the stage efficiency that is linked with, for example, the actual or then theoretical number of trays. One of the scientists, Lewis, he calculated or he provided some formula to link these efficiencies with the number of trays, and that is that stage efficiency of any stage, or overall here, this is overall efficiency of all stages. For example, we have a column and in which let's say there are 10 trays. So what is efficiency of those 10 trays? This E naught explain the overall efficiency of the trays installed in any column. So E naught is equal to something called NT over NA. NT and for number and T for theoretical, like which we say that calculated number of trays. Sorry, and N is actual number of trays. So that means that when we are looking for the efficiency of the trays inside a whole column, that is equal to theoretical or calculated number of trays divided by actual. And let's say the efficiency of overall column is 50%. Then when efficiency is 50%, it means, for example, we have theoretically we calculated that we need 5 trays, but in reality then how many trays will be needed is 10. The 5 divided by 10 will give you this answer, 50%. And later on we will see that for various components, this 50%, I'm just saying as an example, it varies, it can depend on the number of parameters. So due to this, we have to look for efficiency, that how we have to calculate. So efficiency, when you look at this overall efficiency of overall column, including all trays, so that is based on number of experiments. People have observed that it depends on majorly 3 parameters, and those are like geometry and design of the tray. That how tray is designed. In later discussions, we will see that how does this affect, like for example, geometry of the tray. So then there are flow rates and flow path are of vapor and liquid stream. Their flow rates as well as flow path, that from where vapor and liquid are coming in contact or moving through the plates, that also affect this. And then there is majorly the major contributor, which is composition and properties of vapor and liquid stream. That is the major factor which contribute toward the efficiency. So overall, generally here, that when we say that after observing the number of things, if we design our trays in a well structured way and it is well designed tray as well, the flow rates, which will be discussed I think in next section 6.6, that how much should be the flow rate to the column. So flow rates near the column capacity limit. For example, column can handle some amount, and if you are bringing that close to that amount, so in that case mean flow rate is already adjusted. You are not like disturbing the column by bringing maybe too high or too low flow rates. So if flow rates are close to the capacity as well, if trays are properly designed, then there will be the only parameter which will be affecting is the last parameter, and which is about the properties of vapor and liquid stream. So you know that these properties of vapor and liquid stream, they are affected by the temperature, pressure. Uh, Maybe, for example, if you look at these properties, let's say one of the property is, for example, solubility of any one component from the gas stream towards the liquid. Solubility so that it can get absorbed inside the liquid. So in that case, that solubility of components is dependent on the temperature. When you will vary the temperature, similarly the viscosity of the liquid will change, and due to these parameters, when you change these number of properties of the liquid or the vapor, then the mass transfer from vapor stream to the liquid stream in case of absorber, or in case of stripper opposite to this, that will be affected. And when that will be affected, it means the separation which you were looking for maybe will be achieved or not, it depends. Because when you will change these properties, then efficiency of the tray will be disturbed, because due to change in these parameters, that absorption or the stripping can be achieved or not, it depends. So this value of overall efficiency that can be predicted as per discussion in your text or textbook, that is by 4 methods. We can use number of the methods, and the 4 methods are commonly discussed or used. First one is comparison with the performance data from similar column. If we are looking for example, efficiency of some column, that how better it will perform, we can compare it with the efficiency of some column which is already installed actually, and that is performing the separation, and how efficient that column is. We can then say that the column which we are going to design can be more or less closely will be performing in close as compared to the already installed system. For this, definitely there will be needed that if you are designing anything, uh, that you should compare it with any equipment which is performing more or less same kind of separation. More or less same kind. For example, you were absorbing light gases with the help of heavy oil. So next equipment which we are going to design and we want to compare, so we should compare with the similar kind of system which is already installed. So the next method is to use empirical efficiency equations which are derived from data on industrial column. So there are some equations which are called empirical equation. And what does empirical mean?
It doesn't have a background theoretical
Okay,
basis.
then on which basis these are derived?
Experimental basis.
Yes, based on experimental existence specialties, based on the experiments. If you do that, that doesn't have like something as you mentioned. Yes, that does not have any theoretical background. So there will be empirical equation we will look at. They are people have taken the data from the plants, already existing plants which are performing, and by looking at the trends of that data, they have drawn some conclusion, and based on those conclusions, they have provided you with some equation which you can use for calculating the efficiency of the tower. Then there are use of semi-theoretical model based on mass transfer rate. So here they are again semi-theoretical. They will involve actually both. There is something theoretical as well as something experimental, not totally theoretical, not totally empirical. So these are some kind of model or equation which can be used to predict the efficiency of any column. And then there is the last one, that is scale up from the laboratory or pilot plant columns. If you cannot calculate the efficiency when being a design engineer, you are working in any firm and you are looking for efficiency, and out of these 3 options which are discussed so far, so if you cannot use any of those options, then the next method which you can use is to like install a small column on a laboratory scale, get the data, and or maybe the pilot plant scale on still, like this will be a bit larger than the laboratory scale, but still less in size as compared to the industrial column. So if you get that data, then you can just scale up. Scale up means to increase directly. Suppose diameter is 1 feet, and if we take it now to the 10 feet, then what will be required efficiency. So there is some procedure regarding this we will discuss. So let's start with the first one, that when you want to calculate or you are looking for a tray efficiency by using the similar column performance data. So for that purpose, what are steps which are required, or which things you will need is when you are looking for performance data based calculation for observer or stripper efficiency, then you will need is the flow rates initially, like flow rate of feed and product. Mean we should be aware that how much there will be the feed in terms of both liquid as well as the vapor, and what will be their products leaving from the top of the column and the bottom of the column. Like we should know based on the material balance these things, as well the composition at the same time, that what will be the composition, how much will be each of these stream when they are leaving the columns. So then there are pressure and temperature at the bottom and top of column and throughout the column which is already operating. So details of the tray design, that which kind of trays are being used already and what is their like for example seed trays or other kind of trays which we studied, and how many downcomers, and for example downcomer area and so on, rear height, everything that should be known, as well the column diameter, tray spacing, so average liquid viscosity that which you are already operating, and finally overall tray efficiency we will compute with respect to one or more components by using theoretical methods which you have already discussed up to now. Two methods, either it was graphical method or with the help of other method which was called Kremser method. So as you have already seen that either we are using graphical method or the Kremser method, we commonly need these initial three. For example, we should know that what are the flow rates, what are the composition of the things leaving from the tower, for example, how much component will be absorbed, and what are like stripping and as well as absorption factors as well. There was effect of temperature and pressure in terms of like K values. So up to here we usually need these for the calculation of theoretical efficiency. So we will take the data of that tower which is already performing these kind of separation, and by looking at these three data parameters, most of the time you will be able to calculate the like how much or how many there are the number of trays theoretically needed, and then these parameters later on will help you to move further towards the design of a column. So when you have to look at these parameters, but for calculation up to now you know that for theoretical number of trays which we have calculated so far, these three parameters will be helpful. So by using these data, as I already mentioned, that graphical or algebraic method can be used, that we can find the number of stages, number of trays needed theoretically. And because you are performing this work on some existing plant column, so by that you can know that how many number of actual trays are there, because they are known. This is the existing plant. We know that how many trays are actually installed inside the column, and when we have calculated the theoretical number of trays by using all that data, then we can use it to determine the overall efficiency by using the equation which we have seen in last slide. So E naught was equal to number of trays calculated divided by actual number of trays. When you know this, then it means you have found the efficiency of that column which is already performing something. And let's say it is performing the separation of for example, the example which we have already calculated, that removal of ethanol, I think there was ethanol from CO2 stream, so by using water. So if you see that some column which is already existing and performing say such kind of separation, and we want to design the similar kind of column or column which is quite close to this, and that will have quite similar flow rates, composition, as well as operating temperature, pressures, and then we can use this efficiency, or we can consider this efficiency of this existing column for our design of a column, which we are going to perform later on, but these parameters should be close to that which we are going to design. Already existing should be mean actually when you have to compare with something that should be close to your system, maybe not exactly replica of that, but that should be close to the system. For example, your absorbent is heavy oil, so here you should look for some column which is using heavy oil and that is performing more or less similar kind of separation. Not, for example, you are looking for something column which will be using hydrocarbon, this heavy oil, but you take the data of some column which was using water or some acid or base as an like absorbent. In those cases, then definitely this will not help you, or will be this efficiency calculation will not be accurate in that case. So when you look at these efficiencies for absorber and stripper, they are typically low or usually low, and sometimes they are even less than 50%. So when they are less than 50%, it's mean we need definitely double the number of trays which we have calculated or which we have theoretical. So if especially he mentioned that you are using hydrocarbon oil for separation as an absorbent, so in those cases they are less than 50%. So here some scientists, they have taken or collected the data of number of columns which were performing some separation. So they have seen that even for the individual components which you remove with the same column involving same specs, if you look at the efficiencies of the column for individual component, it even varies, and the difference or the variation is actually due to the physical properties of different physical properties of each of the component. As you can see in this table, there are mentioned various components, ethylene, ethane, then up to butylene, and their overall stage efficiency for the column is given when you are performing, for example, the absorption of ethylene, then separately ethane, and so on. So these kind of separation were performed by using the same condition as mentioned here, like the column which was of 9 feet diameter and hydrocarbon absorber, like these hydrocarbons are being absorbed, and that was equipped with the 19 bubble cap trays, and their tray spacing was same, as well as these were operating temperature and pressure parameters. So you can see that even by using the same column for number of components, their efficiency was different. Similarly, I think there are various examples discussed in your textbook in which he has mentioned that if you use same column but the components are different, the systems are different, the efficiency varies. He discussed some things related to the CO2 NaH separation by using water, and then he has mentioned accurately that what are the parameters which are contributing, and those are K values are the solubility parameters, and they are because different for various components which you are absorbing. So due to this reason, the absorption efficiency of the tray or the overall column will be different for various components. So due to this reason, when I was discussing on the last slide that when you want to use the data of existing column, that you should select which kind of separation is quite close to your system, because if for example we say that still there are the hydrocarbon and we are going to design a column for the hydrocarbon, so we can take any of the hydrocarbon which is being absorbed. But here you can see that with any of the hydrocarbon, they all have a different efficiency, performance efficiency for their absorption. So due to this reason, this method is then we can say that not that reliable, because you have, if you want to use the efficiency of the some column which is already existing, then you have to look more or less replica to your system, or that should be too close in terms of operating condition as well as in terms of composition. So due to this reason, then people should start looking for some other method, and the second method which was discussed is the empirical correlation for tray efficiency. And in this some scientists mentioned here, Dreckmer and Bradford correlation. They took the performance data of 20 sets, like from 20 different columns, and they were industrial, observer, and stripper. Now in this case, they didn't do the calculations, or after looking at this calculating the efficiency as per previous method, so they didn't design the columns based on that. But what they did, they took the data and they analyzed it and then try to convert those observation of the efficiency into some equation. So what they did, they just selected, for example, some key component and linked it with the overall stage efficiency and the molar average viscosity of the rich oil. And majorly the collected data was again for hydrocarbon by these scientists. They did it for the hydrocarbon, that when you are using some rich oil, liquid hydrocarbon, heavier oil, for the removal of some components. And the important thing was here, the viscosity was in this range, that was 0.19 to 1.58 centipoise at the mean column operating temperatures. So at the end of the day, after analyzing all the data, they linked actually the efficiency of the column with the viscosity of the liquid. They said that if we know the viscosity of the liquid which we are going to use for designing for absorption in any system, that can be linked with this equation involving some constant based on those performance parameters overall and efficiency of the column. So simply this was very simple equation. First one, which was E naught is equal to this some constant and log of mu L, and this mu L is the viscosity of the liquid which you are using as an absorbent, and its range is 0.2 to 1.6 centipoise. In this range, mean this is valid. If you are still using the, for example, hydrocarbon system, and efficiency of the absorbent of the liquid varies from this, then this equation is not valid. So here, if you want to look at the units, or in which units you will get the answer. Overall, E naught is something in percentage, and this mu L is in centipoise. If we are using this equation, the unit of mu L should be centipoise, and then you can use it. So this equation fits the data with average deviation of 10.3%, means your error will be like plus minus 10% when you use this data in these conditions and for hydrocarbons. For number of systems, it is okay to use. But this equation has two problems. First of all, like this cannot be used for non-hydrocarbon liquids. If we are using water or acid or bases kind of solution for removal of some component, then definitely this equation did not help you to predict the efficiency of the column. At the same time, it is restricted in terms of viscosity data. As I said, that even if you want to use it for hydrocarbon, if your viscosity of hydrocarbon is out of this range, then this equation will not give you a better efficiency. Although you can use this equation, you can calculate the efficiency, but your deviation will be higher than this, or error chances are more. So just to move further, some other people work on the similar line, and then they started thinking to somehow modify this equation or bring some equation which can be used for hydrocarbon as well as for the non-hydrocarbon system. And also, if we can get rid of this viscosity factor, that we can use it freely. So a liquid phase and gas phase mass transfer resistance usually shifts due to the solubility or volatility of species over a wide range. For example, if you are bringing the number of components inside the system which you want to remove, so this mass transfer resistances are definitely different for those components, as well as for example, volatility. If you are stripping some of the components which were already absorbed inside the liquid, so in order to strip those, that is also different. Or if it is extended on a wide range, there are number of values, they are not close to each other, so then these scientist O'Connell found that the equation which was developed, shown on the last slide by Brickmer and Bradford, even that was not like sufficient, or that was not providing the good results for those systems which even involve the hydrocarbon, although you were satisfying this condition of the viscosity. But if there are the number of parameters involved in that, or number of the component which you are absorbing or stripping, then there will be a large number of data, and in that case this equation was not even predicting the good results. So in that case, he started thinking about to modify the equation so that it can be used on the large wide scale data as well as for more component. So what he obtained, that more general correlation by using parameter that includes the liquid viscosity, which they have already included, but also at the same time he modified the equation and introduced some other parameter which were like liquid density and Henry law constant. He said that if we just modify this equation and bring in these kind of other parameters, then this can predict the efficiency in a better way. But some more people worked on that equation, and Admister and Lockhart, they suggested slight modification in the equation predicted by O'Connell, that if we just replace k value instead of Henry law constant. In that equation, if we just replace the Henry law constant, which was suggested by this guy, that if that is replaced with the k value, then we can get some equation mentioned here, that like log of overall efficiency was equal to some constant parameters. And as that guy who initially developed the equation, he has something log of only viscosity, but they introduce other parameters like molecular weight of the liquid as well as density of the liquid, which is absorbent, as well like k value of the component which you are removing, then the same parameter with some other factors. So they said that this equation then can be better used for all number of systems and independent of the viscosity range, as well as can provide better result in terms of efficiency. So again, with this equation, this efficiency, if you use this equation, that answer which you obtained is in percent. So for example, at the end you get answer 48, that means efficiency is 48%. K value for any specific species which we will be concerned about absorbing or removing in case of stripper, and then molecular weight of the liquid as well as viscosity. Kindly have to take care of the units, that these equations are developed based on these units, so the same kind of unit should be used when doing the calculations by this equation. So then actually here you can see in these equation there is some parameter, this k, m, mu, l, and density, and they developed some of the diagram, some of the figure for various systems, and they obtained this curve. As you can see, that this parameter which is given in terms of k value, molecular weight, viscosity, and density, that is related with the overall stage efficiency. And after looking at the number of data of various components, they obtained these data points for various components, and then they have just drawn a journal trend, that this will be the trend if we go for separation by using these components, and what will be the efficiency of the plant. So what they did for this, to perform the experiment or to observe the data which they used included like column diameter ranging from 2 inch to the 9 feet. When they were developing this, for that purpose, this was the diameter considered. You can see there is a wide range of data, like including from very small 2 inch, which is for example lab scale equipment, up to the 9 feet diameter like industrial scale equipment. Pressure range was this one given, as well as temperature range. So liquid viscosity is, now you can see that in this case they have improved a lot. Initial equation was only up to 1.6 centipoise, but this up to the huge viscosity range. And overall stage efficiency, which they considered, that varied from 0.65 up to 69%. As you can see that this data point, which is less than 1, around 0.65, and then maximum up to 69%, various efficiencies were calculated or were observed for the number of columns, number of various systems. So then this was developed. So it's mean, if for example we are looking for the efficiency of some column and we know these parameters, we know that what liquid we are going to use and what will be the operating temperature and pressure. So in that case we know the molecular weight, we can find from the literature viscosity, density as well. If we know that which component we are going to absorb and can find the K value, then you can easily predict the efficiency of column by using this data. But this has also some limitation, and what are those limitations? That this figure, which is shown here, developed by these scientists, that they give the better result when the liquid flow path across the tray is 2 to 3 feet. What does this mean? It's mean, for example, from the top tray, liquid falls to the down tray, and then this liquid starts flowing on the surface of tray. This path mean when it falls through the downcomer, then it starts moving, and then it reaches to the weir and then goes to the next tray. So here this path should be flowing path across the tray, that should be 2 to 3 feet. In that case, this diagram, which is developed based on the previous equation, and that gives you the better result, or that predicts the efficiency in a like we can say accurate way. But it was observed that whenever you use the trace from the theory, as well as we said that from the data obtained from various plants, it was observed that efficiency actually increases when you use more longer flow paths. Uh, that means if your column diameter is large, and then definitely this flow path will increase on the surface of the tray. So in those cases, it was observed that efficiency was even higher. So for example, here is mentioned that with a column which was of 10 feet liquid flow path, although this system will provide you with the only with the 2 to 3 feet liquid path, but if that liquid flow path increases to 10 feet, then in those cases efficiency can be 25% even greater than the predicted by this method. So that was one of the limitations, that if you are using this method, so in that case, because they considered maximum column diameter of the 9 feet, so if column diameter is definitely higher than this, then flow path can increase, and in that case the efficiency predicted by this method cannot be that good. But not good actually, that will be higher as compared to the calculated one. So this here one example is mentioned. But there is another problem with this, that they also assume few things when they develop these kind of equation, as well as this system. So that was that at low liquid flow rate somehow, as well as this flow path of 2 to 3 feet. But if when you have high liquid flow rates, and then long liquid flow paths are undesirable. The reason is initially, if you have like smooth flow on the surface, smooth flow in terms of this, that flow is overall more or less properly distributed, and it is equal on the whole surface of the tray from the entering side as well as up to the leaving side. If liquid flow rates are more or less close, it's mean all the vapor, when they are coming in contact from the bottom tray, here vapor will be entering, so they will be in good contact with the liquid. And when there is a good contact between liquid and vapor, definitely mass transfer will be increased. But when there are the large liquid flow rates, in those cases actually these long flow paths on the surface of the trays are avoided. The reason is that when there are the long flow paths, like if it is greater than, for example, this which they considered up to 2 to 3 feet or more than that. So in that cases, if liquid flow rate is high, that is sufficiently high, so in that case actually it causes non-uniform distribution of the vapor. The reason, for example, here there is a tray and liquid is coming from the top tray. When it enter to this tray, there will be a huge amount of the liquid entering on this side. Then you know that liquid starts flowing on the surface of the tray, and it is collected and then start moving down from the next downcomer to the next tray. So in this case, when there is very high liquid flow rate and liquid is coming from the top tray, on this side of the plate, which is the left side here, so on this side there will be the more liquid as compared to the on the other side of this. So what will happen when vapors are trying to move upward and they find resistance here, because there is a large amount of liquid on this side of the tray, then they will try to find some path which is easy to flow, and that will be the other side of the tray where there is still some less amount of liquid as compared to this where it is just falling down and huge amount of liquid is there. So when vapor will start moving towards that side where there is a less resistance, there is a less liquid, that means they are not uniformly distributed throughout the tray. So when they are not uniformly distributed, then definitely the contact between liquid and vapor will not be good and efficiency will be decreased. Due to this reason, we have to look for something, we call it more than one passes on the tray. So this is some simple one pass system which we usually see, that this is downcomer from the upper tray. The liquid comes on the surface of this tray, then it is collected, and from the rear it moves to the next tray. This is like one pass on the surface of the tray. But here it is shown is something called two pass tray, or we can even have more than one pass. We will look at this. So what we can do is to design the trays in such a way that they can provide you more than one passes on the surface of tray. With this, what will happen actually, what you are doing is, as you can see on this surface of tray, if I consider whole tray, this is complete tray. And if liquid flow rates are sufficiently high, so if you will flow all the liquid in the one way, for example as shown here, in that case in large size of column there will be like not proper distribution on the whole surface of the tray, and due to this the vapor will be not distributed properly and efficiency will go down. So in order to avoid that, what you do, you just reduce the length of flow path, and when you will reduce the length of flow path, in that case that will improve the distribution across the whole tray, and when it will be distributed, definitely a liquid contact with the vapor will be improved. So that is called multi-pass tray system, or we have used multi-pass trays, and that is used to prevent excessive hydraulic gradient. Excessive hydraulic gradient, that's mean, which I already mentioned, that hydraulic gradient mean the amount of the liquid on the surface of the tray. If its amount is varying, that is not equal throughout the tray. So in order to avoid that, we can use these system multi-pass, and that help. And in the big industrial column, the same kind of systems are used. Here in this diagram, it is shown, for example, any liquid which fall from the top, that will just flow on the surface of this tray and towards this direction, and that will be collected. And similarly on the other side, the liquid will be flowing from the main top tray on this half side, and it is collected and starts moving down from here, from the middle both. When they are then just distributed on the lower tray, when it enters from the middle of the next tray, so half of the liquid will move toward this direction and other half will move in the other direction, and then they are still collected and the same path is repeated. So there is the scientists of NL, they provided then some of the system, and that system is like to estimate required number of flow paths if you know the liquid flow rate through the column. So in this diagram, you can see that if we know that what is the liquid flow rate in gallons per minute, then we can also, if we know what will be more or less the diameter of the column, so in that case, then you can decide how many number of passes will be required. So in this, you can see if there are low flow rates, for example here maybe it will be even around 1000 or 2000 gallon per minute, and if column diameter is like sufficiently low, so then in that case you will need still one pass. But if you increase it, for example, you are in this region, somewhere in this region, so in this we can say that if column diameter is, for example, 10 feet, and we know the value, in that case you can say that we will need 2 pass, even more than this 3 pass or 4 pass can be needed. So from this figure you can say that if, for example, 10 feet diameter column is there, here is a 10 feet, and if the flow rate is 1000 gallon per minute, so in that case 1000, here it is 2000, so you can say it will be somewhere in this region here, 1000 in between this, so like we will end up here somewhere. And this suggests that 3 pass tray will be better for the better performance in such kind of the system. So related to this, there are two examples, 6.5 and 6.6. Kindly, I will advise you that solve those, and if you have any problem, just come back to me, and you can ask in any lecture, or even without lecture you can drop email or text. So kindly solve that. As mentioned here, when you solve the example 6.6, so you have to use average temperature. So guys, one thing, definitely we have a lot of syllabus already. I was trying to come up with some of the problem, but that is taking too much time. So as we have discussed the topics, now you can easily go through that, as you already know the problem which I solved for you. But I will say, just take the statement from the book and then try to solve it on your own. Write the steps, that the equation you need, how you have to proceed, as I have done it for the 3 problem for you. If you will start looking from the book directly, he makes sometimes the things more complex for you. So just try to solve it in your own natural way, and they are easy, not that difficult. You can easily go through them, but still you face any difficulty, let me know. Next method is third method, but we will start with that tomorrow, inshallah. Semi-theoretical models. Up to here we have discussed 2 methods for finding the efficiency. First one was, if we know that what is the performance of any column which is already working somewhere, and if you can have your data which you are going to design the plant, and that is very close to the already existing system, you can use the data of already existing system, can predict the efficiency, and then that efficiency you can apply for your own system. But in that case, I told you that you have to be look for some system which is quite close in terms of flow rates, composition, as well as operating conditions to your system. And this method is not that good. Due to this, then scientists predicted some other method, and next method was based on empirical equation. They were still obtained those relationship, empirical correlation, based on the data obtained from various plants, and by looking at that data they try to form some general equation which you can use it for calculating the efficiency of the system. And they were also modified with the passage of time, but still they have means a problem. Some of those we have discussed at the end. So next, due to this, we are going to look at now next method, that is semi-theoretical method, that involves some theoretical stuff, as well as there will be some based on the observation of the performance data from the plants. And then last one will also be discussed tomorrow, inshallah. Thank you so much.